Hello, time flies, and now it's flown all the way to Coursework 2 already. So let's take a quick look at it. The format is the same as in Coursework 1. You get a bunch of imports that you can use, and then you have some problems that you have to solve. So the first part is about 3 different definitions of the less than relation on the natural numbers, and how they are basically the same in this sense. So we're saying that A and B are isomorphic or basically the same. If we can translate from A to B, we can translate from B to A, and we have a round trip property which says that if we start in A, we go to B, then we go back to A again, then we get back the same X as we started with, and the same thing if we start at B. Right? So we're not losing any information by making the round trip. That's in this sense, they are basically the same. So we have these 3 different definitions, that 2 of them are familiar from week 4 lectures. We have a recursive definition. I'm asking you to just see that you understand how it works, prove something about it. We have an inductive definition, where the base case is that 0 is less than n. Check that you understand how this one works. And then we have another inductive definition where the base case instead is that m is less than or equal to m. So the successor case is going to be a little bit different here. Okay, and then we can show that A and B are basically the same by translating from A to B and from B to A, proving the round trip property. We can show that B and C are basically the same. This is a little bit harder, but with some perseverance you can get there. B and C are basically the same. And then you can only show that being basically the same is transitive. So if X is basically the same as Y, and Y is basically the same as Z, then X is basically the same as Z, then from what we have shown already, we should quite easily be able to see that A and C are basically the same. And then we can use that to get a very quick and easy proof that this random number is smaller than this random number. Whereas if we tried to do this by hand, then probably a little bit too quick earlier to see what was going on. But basically what we're doing is we're having one step case for every number that this is larger than this. So here we're going to get 13,000 something step cases if we do this by hand, which seems like it might take a while. So, okay, and the rest of the coursework is about something called Hutton's razor, which was one of the more popular coursework last year, so I've extended it a little bit this year. And it's all about these expression languages, which for Hutton's razor is simple, and here we're making it a little bit not so simple anymore by adding more things. So we have multiplication, and what's important for us is that we have a way to get a value from memory and to store to memory as well. Right. So here are some example expressions. For example, 2 times 3 plus 4. But those expressions such as store the number 7 in memory and then get it again twice and add the results together. Right. But of course, what's important to understand is that these things are just symbols for us. Right? They don't mean anything. Just build them up like this. But in order to give them meaning, we have to define it ourselves. So that's basically the point of the exercise. So in order to do that, we can't just get a number out, because we also have to take this storing and getting from memory into account. Right? So we'll use this particular monad in order to explain what it means to be a value, to evaluate one of these. This says that we get some starting memory in, and then we are not just producing an A, or even a maybe A. So this maybe here is because there might be a type error or something. So we might not be able to produce a value at all. So that's maybe the value, but we also get an updated memory. So if the expression stored something. Right. So the first thing to do is to show that this is actually a monad, which means that we can embed pure things and we can chain things together like this. Do this and then do this, depending on what the first thing evaluated to. These things satisfy some laws, which we can prove. And later we're going to see where these laws are coming from, but for now we can just prove them. They also make some kind of intuitive sense, I think. And we also have these special operations that are supported by this monad in particular. These things hold in every monad. So we can fail, which is a nice option to have. And we could also get the value, so that's getting the value out, or we can put a value which is not getting us anything, not producing anything important, but it's updating the memory behind the scenes for us. And these operations should also satisfy some laws, namely that if you get the value and then store it back again, that shouldn't really do anything. So you haven't actually updated memory, right? You just updated it to the same thing it already was. And if you, in the other order, you put the value and then get it back again, that value-wise should be the same thing as just returning the thing that you wanted to put to start with. But the state might change if you do this, right? So in terms of this monad, this bit is not going to change, but the memory might actually change. Right? So if you want to state that as an equation, you might want to focus on this part of the product. Okay, but the main part here is to actually evaluate these things using this monad. Here's some test cases to see that you've done the right thing. And here are two simple things you can prove about the evaluation. So that was fun, but it was a little bit annoying that we had it maybe hanging around, right? So here's a evaluation where everything also has a type. So you see that addition takes two natural expressions of type natural number, and gives us back an expression of type natural number, etc. The examples look the same, but we just given them the types now. And the only thing that changed now, if we try to play the same game again, is that our evaluation monad doesn't have a maybe in it anymore, because we're never going to fail now. There's not going to be any type errors if everything is of the right type to start with. So then we can define the monad operations again and prove that the laws hold. And pleasingly, this is going to be easier now. It's always nice when things get easier. We can do these special operations again, except we don't have the option to fail anymore. Well, we don't need to fail, right? And we can define the evaluation. And we see that we actually get a value out, not maybe a value. You see in these examples here. That's quite nice. And of course, these two, the typed and the untyped version, they should be related somehow, right? And in particular, if you have a typed expression, then you should be able to just forget about the type, get back an untyped expression. So that's what this type erasure function is doing, and similarly for values and memories. And then here, I'm asking you to think about there's some relation that holds between, if you start with a typed expression, and then you consider erasing it, and you could either erase it and evaluate it in the untyped evaluator, or you could evaluate it first and then erase the value you get. Right? These two things should be related somehow. So if you fill in these holes with the right things, then it should be possible to prove this. Finally, for this section, you will notice when you write the eval function in particular that there's quite a lot of repetition in the things you do. The things you do for multiplication and for addition, for example, is basically the same. You see, they also look very similar here, right? So I'm asking you to go back to this data type and try to factor out the common elements, and then carry that through for the rest of it. And that might help you with the rest of the coursework as well. You don't have to do it, you'll be fine. Even if you don't want the 2 marks, but you just have to type a little bit more if you don't do it. So here in the next stage, we're going to take our expressions and we're going to compile them to stack programs. And the stack program is a sequence of instructions like this. That are instructions for manipulating a stack. So we have instruction for pushing an element to the top of the stack, an instruction for popping the topmost element, an instruction for adding the two topmost elements and putting the result back on the stack, and we have special instructions for loading and saving to memory just to match the expression that we have. And we also have a branch instruction which looks at the topmost elements which has to be a Boolean, and then depending on if it's true or false, we're going to continue like this program or like that program. The important thing here is that these programs are indexed by the list of the types of the elements on the stack before and after execution. We see that push is going to start with a sum stack, well, sum types t's, and then it's going to be one more element afterwards, which is the type of the thing we pushed. Pop goes the other way, you have a non-empty stack, and then it's going to remove that topmost thing. Addition requires that there is at least 2 natural numbers at the top of the stack. It's going to put the natural number back, etc. That's quite helpful when you write programs, because it keeps you sane, and it's also nice in order to relate it to the typed expressions that we had. So before we get started on these things in earnest, let's see if we can print them out. So it's a little bit easy to read them. These branches in particular can be hard to parse otherwise. So I wanted to print them like this, where you add more indentation every time you get to a branch. So then you see that it's very easy to see that this thing corresponds to this nested branch, and not like this, right, which is it. But the main function here is really the compile function. It takes an expression and compiles it down to a program which claims that if you start with t's on the stack beforehand, then you're going to get one more element on the stack, and it has type t, it's the same type as this expression. Right? So what we wanted to do is we wanted to add instructions that are actually going to evaluate this expression and put it at the top of the stack in the end. In order to make that formal, we have to define what a stack is, because we just talked about the list of types so far, right? So here we define it. We're saying that the empty stack has the empty list of types on it, and a stack which has this list of types on it consists of a value for the top element and then another stack. The configuration now is given by 2 things. It's a stack, which might change, we might push and pop things to it, and it's also the state of the memory at the moment, which is just a natural number. And the point now is that the run function for a program turns a configuration for this t's into a configuration for t's prime, which was the after state of the program. So we have this pleasing coincidence between the program and the configuration transformer. And it has a nice equation that we want to be true, which says that if we start with an expression, then compile it, and then run that program, then we should get the same thing as if we evaluate the expression directly. So this evaluation has nothing to do with stacks, etc., right? So if we evaluate it and put it at the top of the stack, and similarly if we evaluate the state for the memory. So that's linking compilation, running, and evaluation in a nice way. So that's nice. When you get to this point, you can also comment out the rest of the file. You go to the very end, press Control and End. Then I delete that line. The reason I have commented out for you is that some things here actually talk about the run function. So I'll do that again. You're going to get a bunch of yellow here because the run function has not been defined at this point. So I thought it would be annoying to see that all the time, but let's ignore it for now. So in this section, we want to add one more layer to our compiler. We have a compiler, right? We can run it, but now we want to add some optimizations to it at the level of programs, because that's where the fun optimizations are. If we start from the bottom, this is the idea that we should take a program which turns t's into t's prime on the stack and turn it into a program which does the same thing. So it shouldn't change the types of the things on the stack. And in fact, it shouldn't change the run the actual runtime of the program at all. So I wanted to show that all the optimizations you do actually preserve what happens if you run them. But how are we going to implement this? Well, we're going to implement it via this optimize worker, which takes a list of single optimizations that we are proven correct. It takes a maximum number of iterations to try to optimize things, and then take an input program and turns it into an output program. Right? And what you should do is you should take this list and apply all of these optimizations to the input program until nothing changes anymore, or the maximum number of iterations has been reached, whichever one comes first. So in order to do that check if something changed or not, you also need to implement when two programs are equal, which here has been formulated in a slightly funny way because the programs have seemingly different types. So we can say that maybe the types are actually the same, and then the programs are also the same. But we always have the option to return nothing, right, if the programs are not the same or the types are not the same. So that's something you need in order to define this function. We want to do this check if something has changed or not. But how will you then define single optimizations like this? Well, there's an example up here that you can look at. This is quite a simple optimization. It's just removing no ops from the program. So if you have P followed by a no op, then what we're going to do down here in the end is we're just going to just keep the P and optimize that as well, just in case. And then here's the correctness proof for it. It says that we optimize P and then run it. That should be the same thing as just running the original P. So it shouldn't change the meaning of running the program. It should just be more efficient. And by efficient, we mean has a smaller size, where the size is very naively defined here. Just the number of instructions in the program. And depending on how much you can improve this, the more marks you will get. So you have to come up with your own optimizations. I've given some suggestions here, but it's really up to you what you can do. But of course you have to prove them correct so that you know that they really are optimizations. I hope you'll have fun with that. Have some fun ideas for what you can implement. All right, good luck.